the second week of the school, and the first lecture this week was Matthias when he talked about the sound problem in quantum Monte Carlo. And that was for a reason that we put this at the beginning of this week, because this week we are presenting a lot of standard techniques beyond quantum Monte Carlo that do not suffer from the sign problem, and as such are interesting in their own right. So these techniques are exactization, which I'm going to teaching, which is Brian's doing, and I will talk in this short lecture today about series expansion, which is yet another technique that doesn't suffer from a sign problem. But as you will see, all these other techniques have limitations in their own right, and well, very specific to their own approaches. Now, there's lecture notes to these lectures. Unfortunately, when these hands-out are printed, some bug made its way into the copying process. There's 40 slides in my lecture. There's only 20 slides in the handout, and to make things even more confusing, it's every other pair which is missing. So basically, these notes are probably more confusing than helpful in following the structure. They were also upside down presented, so most of you are looking actually at the right end of the lecture. So this is not how we start, how we finish. But probably these lecture notes are not going to be very helpful to them. So I will talk about linked class expansions here for quantum many body systems, and this is the overview of the lecture slide, which is also not in your notes. So I will give a brief introduction to series expansions in their more general context, because it's a very old and well-used technique. And then I will make my way into the formalism and talk about linked cluster expansions specifically, and see how we can derive these. I will focus mostly on zero temperature expansions in this lecture, but a lot of the technical stuff that I'm presenting can be applied in many different contexts. I'll go through a number of specific examples to show you how one can do these calculations, and give more general hints at what might be calculated in the end. It takes us to harder problems and the example problems. There's a lot of variations in this approach, and I will mention a lot of alternative approaches and variations of the overall scheme of this series expansion technique towards the end. So series expansions have been used a long time in classical statistical mechanics, and one simple idea is to make a high temperature expansion that is expand the partition function of the classical system in the inverse temperature. So this has been done quite extensively, and the merit of the series expansion was that doing these series expansions, people saw the first indication of universal exponents, and it was that development eventually triggered other techniques to be formed, such as the renormalization group and the discovery of universality. So series expansion has been playing a crucial role in the development of classical statistical mechanics, and have their roots in these very old days. More recently, series expansions have had a revival in starting in the late 80s, and people started to use these for quantum systems. And more recently, people have used zero temperature expansions, and that will be the main feature in this lecture. And these things have been playing a crucial role today in those hard problems where we cannot do Monte Carlo, and low-dimensional techniques are probably not good, such as frustrated magnets, and I will discuss this later. So here's the main equation of this talk. So not the one I said yesterday, but one equation you have to solve. This is the starting point of a series expansion. You have some Hamiltonian that you would like to analyze, or some given lattice model, for instance. It's a quantum system. And how could you do a perturbative approach to investigate this problem? Well, you can take this Hamiltonian and split it into two parts, and you say, well, some part of this Hamiltonian I like, and I should solve it. So we call this unperturbed part, and that part gives you some basis to work in. And then the rest of the Hamiltonian we treat as a perturbation. Okay. So this starting point can be varied. You can choose different unperturbed parts of your Hamiltonians. You can start different patterns of ground states and try to make, work your way back to the original Hamiltonian of the system that you want to study. Well, so we will see examples of these calculations in all kinds of contexts. But so this introduces a parameter lambda, which parameterizes the perturbation. Lambda does not necessarily have to be small, and you come back to the original Hamiltonian. Okay? And the goal is to write in an expansion of some properties of our system, such as the grounded energy, as a function of this perturbation parameter. And the goal is to do this perturbatively and to do it way beyond what you guys can do, doing it by hand. So we're interested in writing down a high order series expansion. High orders like second order, but whole 20th order. Okay? And we want to do this in a way that all these coefficients in the expansion are calculated analytically exact. Turns out that doing that by hand is impossible, but doing it on a computer is possible. And that is also what distinguishes these calculations from stochastic things. When Roger was talking about stochastic series expansion, he was writing down an expansion from the grounded energy to 5,000 orders, but he was calculating those 5,000 coefficients in the expansions some error. Well, this is a technique that will calculate the first 20 orders of that expansion exactly. And so the difference also is that the SSE was again a high temperature expansion, and this we want to do here is a zero temperature expansion. So we want to calculate something like the Taylor expansion, and we want to do this in an elegant way. And here's how we will try to do this. And as an example system, we will look at a very simple one-dimensional system, a spin ladder. So this is two spin and a half ladder. So spins are arranged in this ladder geometry. There's rungs on this ladder, and there's homes which direct these spins. And one way of studying this ladder Hamiltonian, our Hamiltonian might be the one, maybe the one that you're interested in, so that you have isotropic couplings along all these directions in the ladder between the spins. And one way of splitting this problem into something that we can solve very easily, and then treat the rest of the Hamiltonian perturbatively, would be to go to a limit where we say, well, we make this one coupling here, very strong, we set that to 1, and the coupling along the ladder is set to 0. So that's the operative Hamiltonian, that's the Hamiltonian describing decoupled dimers, and solving this dimer Hamiltonian is very trivial. So there's a singlet and triplet state. And then we started coupling those singlets and triplets along the ladder into the full Hamiltonian. So that would be an example of taking a Hamiltonian that we would like to solve and splitting it up into a part that is trivially solvable, at least in some basis of dimers, and then treating all the other couplings as a perturbation. And for lambda, so we assume that lambda is small and we write down the expansion. In the end, we actually in the limit that lambda actually turns to 1. Go back to this isotropic limit. And you will see that we can actually do that. So how can we, taking this example system, how can we go ahead and start writing down an expansion of this grounded energy for this system? So here's how we can do this. So this is a part of the Hamiltonian that we treat as a perturbation. So it's a coupling between these rung spins. And well, the first approximation we can just, the first thing you can do is you can write all these terms as interaction terms which act on these buckets. So we enumerate them, H1, H2, H3, H4, which interact between the first and the second dimer, the second and the third dimer, and so on. Now, with each of these terms in the Hamiltonian, and the Hamiltonian is one for the infinite system, we can associate a coefficient lambda k, and now write down a expansion in all these parameters lambda k, so all these contributions of the different terms in the infinite Hamiltonian, and write the energy in this expansion just as a sum of parts that are contributing for every little piece in this expansion. So the energy can be written as a sum of contributions that come from individual combinations of these lambdas. So I can turn on the lambda here, say this part contributes, and here's a part that contributes, and all these things that contribute to the expansion. So far we haven't done anything, we have just rewritten our energy in that form. Now, if you look at this expansion and you're asking which terms are contributing, you start to see little diagrams. So if only lambda 1 contributes, we'll have a diagram which looks like this. So you will only have a coupling of the first and the second diagram. Or if you have lambda 3 contributing, so being in this constant 1, and you will see that this guy contributes. And it might contribute to higher orders. So, there's some recursive things going on, so you go back and forth with this pair of dimers, for instance. But you also might have, in this expansion terms, look like this. You have two connected brackets, and the perturbative expansion, you see that they're both contributing. So we call these little diagrams that are contributing to this energy, we call those clusters. Okay? And then you have a lot of these clusters that you can write down. Here's just a set of examples, and this complicated sum here can then just be rewritten as a sum over all these clusters. So the sum over all these diagrams, and every cluster is contributing in a particular way. And how we will calculate these contributions from each individual cluster, we will see later on. Okay? So here's what you do. So you take our original problem, you have some perturbation that you want to treat, such as interaction between these dimers, and you translate that into a sum over diagram. So these diagrams are all clusters, which tell you which part of the sum you're looking at. Okay?
What is the of k?
What is what?
The small of k in the sum?
So that's the order in which these things are contributing. Yeah. So the lambda k says, so it might contribute once, so it might contribute twice, so it might contribute, 11 times. Yeah. So.
The small is energy of.
So this little e here is the energy that is associated with these powers here. So it's the energy that you get if you have two orders of h1, for two orders of h2 and one order of h3. Okay. So that's something you can always write down. And now the whole goal is to go through these diagrams and calculate their contributions in an efficient way. And the first thing that you notice here is that things look already a little complicated. You would like to simplify the way that things are contributed in the most powerful way.
So, I'm sorry, another question. Typically, in perturbation theory, you take these denominators, 1 over. Now, you did so in denominators, so probably somehow you rewrote your expansion.
Oh, I haven't done any perturbation theory so far. All I have done was an expansion in lambda. Okay? So the way that this perturbation theory that you're talking about will contribute is you actually calculate what this cluster is going to contribute. Okay? So far we just said the cluster is going to contribute something. Okay? And whatever it contributes, we will add up. Okay? So it's all diagrams so far only, and what their associated values is that is okay.
So
okay.
Making sure I understand, the lambda k will be like the original lambda that you have for the interaction for each of them, and you're going to take each of them to one at some point.
Exactly. So now I'm treating every term of the Hamiltonian individually. So instead of saying I have one lambda, which is saying that the whole all these interactions are connected, I'm starting with the most complicated case, and I'm saying that, well, probably this H1 is contributing a little bit more than, H2, a little bit more than H3, and, H4 is a little bit more again. Yeah? So that's the most general case, and the next step that I'm going to take is I'm going to throw that away again. I'm saying, well, all these lambda k's, I can only set them all to the same value, that's the lambda. Okay? So that's very much in the way that the Hamiltonians were written at the beginning, that they are contributing all the terms, all the interactions between different dimers equally. Okay? But the most general way of doing this would be to individually treat these things. So instead, what you will get from a picture like this are diagrams like those that no longer identify whether this plaquette is the first, second, or third one. Okay? And then similarly, these pairs of plaquettes, you don't say whether it's the first two or the middle two and so on. Okay? So this brings us to the question that we're starting to sort. Yeah.
So each of these h's should contribute some up to infinite order in the expansion.
Right? Exactly.
But then, so why are you grouping them together?
So every h contributes. So we will see that every plaquette contributes, and it can in principle contribute all orders in lambda. but so does this one. Okay? So the point is that we are assuming now, when we set these lambda k's equal, is that the contribution of this cluster here and that cluster here for energy is the same. Yeah? So, and then we don't want to do our calculation twice, but only once. Okay? So before I had these two redundant pictures. Yeah? So if lambda 1 and lambda 3 are equivalent, these two things will contribute exactly the same thing. And if lambda 2 and lambda 3 and lambda 3 and lambda 4 are equivalent, these two pictures are going to contribute in the expansion to the same value. Okay? So setting all these lambda k's equivalent means that instead of considering every possible diagram, I start looking for diagrams that look alike. And so here's, in this specific example, they look alike like this. So 1 plaquette, 2 plaquettes, 3 plaquettes are contributing in that sum. Now, the example that we're doing here is a particularly simple one because it's a one-dimensional example. So the more general case is that you have, these diagrams where they can be more complicated. And then you have, the question that you're asking is, are these two diagrams equivalent? And they're called topological equivalent. And if they are topological equivalent, then they will be contributing exactly the same stuff in the series expansion. Okay? So for this particular cluster, pair of clusters, you see that the problem is much more complicated in saying whether these two things are contributing the same to an expansion or not. So while you try to find out whether these are the same, I will explain what this actually means. So they're the same if two clusters are topologically equivalent. If you have a mapping of the vortices in this cluster to the vortices of that cluster, such that this cluster becomes that cluster, so every bond in the first cluster, the bond in the second cluster gives a solution. Yeah? So indeed there is such a mapping, so it's done color coded here. So these clusters are exactly equivalent, but you see how hard that is to find. Okay? So once we have topologically equivalent clusters, like this example, then they will have the same contribution.
Color coding doesn't quite work.
Oh, really? So,
There's no yellow one.
okay, so sorry, this color and that color are supposed to be the same. So here's the homework.
Does the top one equivalence include the different bonds here?
So what you're asking is if there's a coloring on the bonds, then you want to take that into account too. Yes. So in this example, all the bonds are black, and no vertices are colored. So this it would be a red bond, and it should be mapped to a red bond. That's true. Yeah. So. Right.
Isn't identifying manifolds like this needs to be outside of
What?
Isn't this known to be hard or needs to be hard?
Yeah. So I'm coming back to that. So this is so if you're asking, what's the complexity class of this problem, you will find it very hard. So later on you can ask this question again: is it practically hard? Yeah. So are you ever going into the limit where this is really hard? So where you have 50 vortices in these graphs, are those actually ones that you will be able to consider in your expansion? Okay. So the answer would be no. So while this is from a computer science perspective, finding these mappings is extremely hard. For large graphs, for those practically purposes that we have, being limited by other things, the graphs that we will be looking at are smaller, and we can find these isomorphisms relatively fast. It's still a tricky problem. Good. So once we start taking a perspective at these diagrams, these clusters, and seeing those are equivalent, we can start amassing them and take one representative out of each group of clusters that are topologically equivalent and call it for instance the canonical clusters, this C is a tool here. And instead of doing calculations for all of these diagrams or clusters, they're doing whatever calculation we're doing in order to do that expansion just for this representative, and then we are calculating a multiplicity factor which shows us how many diagrams are in this class. And so how many diagrams are in this class? Well, that very much depends on what you're actually looking at. So which problem you're looking at and which lattice, for instance, you're looking at. So for instance, if your diagrams look like this, so you have a two-bond diagram, which in the language of our spin ladder that we have, because every point here would be a dimer, and every bond would be two coupled dimers. So then you see that if you take a set of square lattice as the underlying lattice instead of a one-dimensional arrangement, there's a lot of ways of taking this diagrams and embedding it into the square lattice. Okay, so so what I've done here is that in this diagram I fixed one point and colored that, put it as the iteration of this lattice or something, and started to embed it, and then you see that this way, stepwise thing and so on. And then you count this, and then in this case you probably have 12 of these embeddings. So that means that this representative cluster that you can take, for instance this one, you would multiply whatever contribution it generates 12 times in order to have it contribute to the sum. So for instance, if you're calculating this grounded energy, now of a diamond holding in a two-dimensional arrangement, we would multiply whatever contribution this small cluster contributes to the energy 12 times to calculate its overall contribution to the energy. Now, there's potentially an enormous reduction here at play. So already here you see that instead of doing something like a dozen calculations, I could reduce myself to just one calculation on one representative out of this set of calculations, and then just simply multiply my result. And these multiplicative factors will actually explode as you go to larger lattices, to larger diagrams and different lattices. So here's this potential gain that you can have in an expansion where you treat only these representative diagrams. So here's three different lattices, which are different coordination number, and so as enumerated here is a number of clusters which have n bonds. So the cluster which has just one bond, that's just one guy, which on the square lattice you can put in four directions. The triangle has a sixth direction, and so on cubic lattice. And now, as you consider that example that we just had, a diagram which has two bonds and three vertices, well, there's already two examples of that, which have 16 embeddings on the square lattice, a much larger number on the triangle and cubic lattice. And then as you go to 10th order, what you will find is that if you look at diagrams which have 10 bonds, well, there's only 679 representative canonical clusters, which are representing a much larger group of diagrams that you would have if you wouldn't do this trick of going to the representatives. There are only 2 million for the square lattice, and then for the much higher correlation of the triangle lattice, there are only almost 300 million diagrams. Okay? So calculating 300 million diagrams is something no graduate student can do, and also no computer can do in a reasonable amount of time. But you will be able to actually do these other calculations. And instead of doing 750 million calculations here, you can do 1,000 calculations. Okay, so the first trick is to go and instead of taking every possible calculation, amassing them in their representative calculations. Okay, so so this is the idea. Okay. Now the next step is these calculations that we are going to do. Are these finite size calculations that we're doing, or are these calculations that are actually more effective? Well, it turns out that you can do these calculations directly with thermodynamic limits for the expansion of something like the grounded energy that we are calculating. You can calculate directly in the thermodynamic limit. So for the infinite system, despite the fact that we're looking at small diagrams and small clusters. Okay, so that's again assume that we have some observable like the energy P. That we calculate for some of these clusters, for some of these diagrams, just see. What we will be adding up is the contribution of all the cluster parts that are part of this larger cluster. So all these subclusters C prime, which are part of the cluster. Now, you can rewrite, of course, this sum as a contribution which is originally from the large cluster, plus everything that comes from smaller clusters that are part of the larger cluster. So, and in particular, this allows you to calculate the original contribution of some cluster in this expansion in the following way. What you're calculating is whatever contributes from this cluster, so this is, for instance, the energy that this cluster tries to contribute, And then you subtract all the parts that come from smaller clusters that you can embed in this larger cluster. So here's a picture which tries to show this. So if your diagram that you're looking at, asking what is this packet of four parts contributing, for instance, to the energy. So you're calculating the energy on this cluster, you'll see that the contributions to that energy on this cluster are coming from all these smaller parts, can be all embedded into this cluster. Okay? So you can calculate the original contribution of this cluster here by calculating the energy on this cluster and then subtracting all the energies of these smaller clusters. Okay? And that's called subcluster subtraction, and it's extremely powerful because it eliminates all these lower order contributions. And in the end, what it distills is the contribution that is actually original to this new bigger cluster as compared to all these smaller ones. And it's only that part that will contribute in the end to the overall sum. So we sum all these cluster weights to calculate the energy in the thermodynamic limit. And that's how we actually get to the thermodynamic. Every cluster only contributes a part that is actually new coming from this cluster, because everything that we have calculated before for smaller clusters will get subtracted. Okay? Is this clear? Okay. So this is the crucial part. We're subtracting these parts. So if you do this in a perturbative scheme where these cluster weights are calculated, for instance, by perturbation theory again, then we will see that these lower order terms will be eliminated, and I will go through an example in just a second. Okay? And we directly obtain the result in thermodynamic limit. Now, there's a trade-off here. So no longer do we have a finite size effect. So Andreas was talking about when he talks about excitation. There you are limited to doing the calculation only for the biggest cluster, and then you have some calculations for small clusters. So you're trying to extrapolate to the thermodynamic limit in doing that. So this approach here is different, in that for the larger cluster it doesn't calculate just the contribution of that cluster, but only the original contribution of that cluster to the thermodynamic limit. And so what you are trading is finite size scaling, which is the extrapolation, which is something that we will see here. Is the fact that the series that we are calculating in the end will be only a finite order series, and we will want to extrapolate that. So we are trading finite size. There is this series extrapolation. Good. Now there's one more step that is interesting. You can eliminate a lot of diagrams in this calculation. Then we go back and look exactly what this subcluster subtraction does. And what it allows us to do is to throw out all disconnected clusters. So here's a disconnected cluster. So this cluster C is made out of these two clusters A and B, which are not connected. So is this cluster C contributing? And the answer is, well, no, it's not. So for a disconnected cluster, the contribution of a cluster can always be written in a way that there's a contribution from its subcluster A and a contribution from its subcluster B. And the effect of that is its variable will vanish, because now we can disclose the mass of these cluster weights again. So for this cluster C, its contribution is whatever you're calculating on the cluster C, like its energy, minus all the contributions coming from clusters which are smaller than C. So know that this is all subclusters which are smaller than C. But then as you divide this into those parts which are coming from cluster A, so some energy which comes from cluster A, minus all the subclasses, and now we can look again at the subclasses that we're looking at, and then we will find some which are only part of A, okay, and some which are only part of B. And now there's an equaling here. So taking everything that cluster A is contributing and subtracting everything, including the contribution of the original cluster, we just eliminate this part of the sum, and the second part will also be eliminated. So in the end, such a cluster cannot contribute. Okay? So all these disconnected graphs, you don't have to consider. And so my long list of how many graphs there are, those were only the ones which were connected or linked. So this is why this is called the linked cluster graph. Okay?
This is only for observables like magnetization of energy, but not for correlation functions.
You would think, but no. So we can calculate everything. So the extensive property has, the grounded energy, but we can also calculate impedance things like the excitation gap. So how we do this, I will just show you. Now, so this was all very theoretical. We have heard a lot about these different diagrams, and as Brian already mentioned or saw, there's a lot of connection between taking care of these diagrams like graph theory. That's indeed true. So it comes in three different places. So the first one is that you want to generate all these clusters, all these graphs, which you can put onto a particular lattice. Turns out that is already a tricky problem. So if you try to find, this exercise, all diagrams which have, 7 bonds that you can embed in the triangular lattice, you'll find it's a really tricky and hard problem to come up with all of them and be sure that you found every single one of them. Okay? So you can try to do this in the lowest orders. Try to find all third order graphs, try to find all fourth order graphs, and you will find that it quickly starts getting a massive problem that being sure that you found everything and haven't double counted these things. So the first thing is generation of these clusters, which is graph theory problems. So you're generating them all, and then you have to compare them, which brings us to the second problem that you want to find these equivalence classes of clusters. So you want to find a fast way of identifying isomorphisms between two graphs, so two clusters, as a topologically equivalent. So in computer science, that's a well-known problem, trying to find these equivalence classes, and it's a pretty hard problem. So for very large diagrams, it's not going to work in a very short time. But as you saw, I could enumerate them all up to 10 order very easily. If the number of bonds in this diagram is 10, you're not in the regime where this really hits you big time that this is a hard problem. And the last thing is, you have seen that eventually we're interested in getting these multiplicities right of these clusters. One way is that we generate exhaustively every single cluster that is possible for a given lattice geometry. Or for some other reason we already have those representative diagrams, and then we want to embed them on that particular lattice. So that's what's called subgraph embeddings, and it's another really hard problem in computer science. So taking one particular graph and trying to embed it into another much bigger graph is also very hard. And so these are the three things that we're interfacing in this technique to well-known computer science problems. And while they're hard in their own right, they're actually not hard in the context of these experiments, because we're always looking at small diagrams in the language of computer scientists. Nevertheless, we should make use of all the knowledge that has been generated in that community in order to deal with these diagrams. And something that you have already seen is when you install ALF, you all get the Boost graph library as part of that. This is what is used in the ALF lattices to describe a lattice in a more general form. So the Boost libraries is something you want to all be aware of. So it's a more general C++ libraries, and one part of it is a very nice graph library that allows you to define lattices, so graphs, or in context of these lattice models, we call them lattices. And in its original form that is discussed in this book, the graph library is only some very smart way of bookkeeping, and it doesn't have all these nice algorithms that we would need in the context of these cluster experiments, like isomorphisms and automorphisms and special labelings and sorting of graphs. But there have been implementations by computer scientists that were very, very efficient in doing these things, despite the fact that it's a hard problem. And more recently, this young fellow, Lucas Gamper, has done the implementation for the Boost graph library, and I hope it will go into the library quickly, so that it will be publicly available. So this was the first part, which dealt with lots of diagrams, and sorting these diagrams and then taking care of them. And now we want to perform an actual calculation. So let's try to calculate something for a given diagram. And very much in the spirit of these expansions, what we are going to do is a perturbative expansion. So now again, we are looking at some quantum system, and we look at it at 0 temperature, and we would like to calculate, the energy, for instance, of some diagram, as in the case of our spin ladder, and calculate its contribution to the thermodynamic limit. And one way of doing that is now to use perturbation theory. And in this particular case, it's very simple. It's just regular Schrödinger perturbation theory. So you keep track of your grounded energy and the grounded wave function, and you can iteratively calculate order per order of this energy on a cluster that you have prepared. So here's our example of the spin ladder. So the simplest graph that we can write down is our unperturbed Hamiltonian, which is just a single dimer, and we can write down the grounded energy of that dimer to all orders in the perturbation. Well, because there is no perturbation in this graph, it's just the energy of this singlet state on this dimer, and that is a contribution of that single graph to the thermodynamic limit. That's the unperturbed limit. And now we can take the first graph, which is the one which contains two dimers. So the maybe that I used before, that's a graph which has a single bond. And again, we can ask, in this coupling, which unfortunately now is called X and lambda, in this coupling between these dimers, what's the grounded energy of that situation of two coupled dimers? And well, now we can do this derivation theory as you know it. So I should do derivation theory, but now we will do it on the computer, no calculated order by order on the computer. And so here this is done up to fourth order. And so this is the contribution that you will get when you calculate the energy on this particular cluster. And now here's the crux. So you already know that this energy that you're calculating on this cluster is going to be written as a contribution of this cluster plus some contribution which comes from all its subclusters. And so the subclusters of this cluster are diagrams like this, and there's two of them in it. So the series that we are calculating perturbatively as the contribution which is original to this cluster, plus twice the contribution from the smaller one. So now we go ahead and calculate this part here by taking this series and twice subtracting what we have found up here. So you will see that this first coefficient in the first term in this expansion will just fall out. So the new contribution of this second cluster starts in second order, and then has a third order and fourth order piece there. And now we can continue and look at a diagram like this that has three dimers. So in this language that would be a diagram which has two bonds connecting three vertices, these three dimers. And again, we can perturbatively calculate the energy on this cluster, and do this again up to fourth order in this coupling between the dimers, and get a series like this. And again, we are aware that this is now a contribution coming from this cluster originally, plus twice times, 2 times. I can embed this one into this one here, and then 3 times the smaller one. And now what you can see again is that the original the time that you have here for the cluster, you have a first in a zeroth order term, which is the second 3 times the one of this one, so it will cancel as you're subtracting subclusters. And so will the second order contribution, which is subtracting twice the one that you have calculated up here. So the first time that this cluster is contributing is in fourth order. Okay?
What happened to the speed?
So there's no cube term here. So there's a cube term here. That's a good question. So there must be a cube term here in branches. Okay? So I'm so sorry about that. So it's probably wrong. So the pattern that you will find in the end is that these clusters which have so this cluster has 2 bonds, will contribute to second order. This cluster has 4 bonds, will contribute to fourth order, and so on. And then to go to the thermodynamic limit, what you will do is calculating now the expansion of the energy, not for a particular finite cluster, but for the infinite system. So for the infinite value, just as many ones as possible. What you will now do is that you add up all these contributions coming from the individual clusters. Now, for the case of this one-dimensional arrangement, the multiplicity of all these clusters is always 1, so this is a boring sum. So these lattice constant, the number of embeddings that you can write down, is always 1. So all you do is you sum up all these orders. So you take this guy, you sum it with this series and add it to this series. And then you get an expansion of the Untitled energy in the thermodynamic limit, now up to 4th order. And now this whole scheme can be repeated, and you can go to much, much higher orders. Yeah? And in the end, you get a nice calculation of the Untitled energy. Now, you can do much more than calculating just things, simple things like the Untitled energy. This question of Stefanos. Can we go beyond this? Well, we can. So now let's consider the case that you want to look at the first excited state. So in our spin ladder, that's flipping one of these spin signatures on the diamonds to a triplet. So the triplet excitation, and then this triplet excitation can start moving up and down the ladder. So it gets stressed, which is the effect of turning on the couplings between these bonds. So the question is, what's the elementary excitation of this coupling system, and can I calculate the excitation spectrum, and can I do this using this framework of the cluster expansion? The answer is yes, you can do this, but it's not that obvious in the beginning. So what you would like to do is calculate an effective Hamiltonian in the subspace of these excitations. So as we go back to the picture, we can take this excitation here and put it on many different locations in this ladder system. Okay, we would like to calculate an effective Hamiltonian in that subspace of putting the excitation on different positions in my ladder system. Okay, so for a given graph, which is just a subset of this, so if I have, for instance, a graph which has 4 of these dimer bonds here, there's 4 different places to put it, so I have 4 subspace of these dimer configurations, in which I would like to calculate an effective Hamiltonian. And calculating this effective Hamiltonian, I want to do some transformation to my original Hamiltonian describing the whole system, so that I decouple this effective Hamiltonian from the rest of the system. Okay? Now it turns out that this situation here does not have a direct series expansion, so it's not an extensive problem. Yeah? But what turns out, what has a cluster expansion here are the irreducible matrix elements of this effective Hamiltonian. So what is that? So what's an irreducible matrix element? So what you're calculating is the hopping of these dimers sitting on this ladder system, and that's something you want to calculate. But there's also other things that go on in perturbation theory. For instance, there's some ground state fluctuations of the system fluctuating. This is the stuff that you have calculated before when you calculated the ground state expansion. And subtracting exactly those parts, so the fluctuations of the ground state, from this one body situation, so the one particle excitation situation, it gives you the irreducible matrix elements. And for those, you can actually write down a series expansion again. Okay, so you can take these matrix elements, and for these matrix elements, and write down a series expansion. Now doing degenerate perturbation theory to calculate. In the end, what you can do step by step is calculate this effective Hamiltonian order by order, decoupling it from the rest of the system, and then having this effective Hamiltonian in a situation that hopefully can diagonalize that effective Hamiltonian and thereby solves the problem. Now, for the simple example that I showed you, like the spin ladder case, you can actually solve this effective Hamiltonian by the simple observation of the variant, and what will solve them is a simple Fourier transformation, and then you can calculate its energy eigenvalues. So here is the solution of that for this spin-and-a-half ladder. What you will find is there's this triple excitation which gets stressed as you turn on the coupling along the ladder, and will start moving around, and then it's called a triplon. And the triplon will acquire some dispersion, and you can calculate this dispersion up to very high orders in this this coupling along the ladder. High orders again, like 10 to 15 orders in that coupling. So way beyond everything you might be by hand. Now, you can go further beyond this and calculate a situation where you not only have one particle excitation, but you can put in two particles. So you can put in two of these triplet excitations into the lattice system, and then calculate the effective Hamiltonian. So further transform your original Hamiltonian in a way that you start now to decouple this two-particle sector from all the rest of the system, and calculate all the again irreducible matrix elements that come to this effective Hamiltonian. So what is an irreducible matrix elements here now? So now if you have two of these triplet excitations in the lattice system, there's always a contribution which just comes from one of them. So this is what you have already calculated. So you subtract that, and then there is a ground state fluctuation, which you again subtract, and what you're left with is a contribution which only talks about these two excitations interacting with each other. And in the end, you get some effective Hamiltonian in the sector of two excitations, and then you have to solve that. And there's you can do that again numerically.
Question about the previous slide. How is this triple excitation different from the excitation in one chain? What is it saying?
So how is it different from a spin one state excitation? So this is so the difference is it depends of course on the coupling on the dimers. So if you have an antiferrometric coupling on the dimer, that's different. It's a different situation than a Hall chain. Okay, so you can so this situation that's shown here is for antiferrometric couplings both on the dimer and along the ladder. Then you get a dispersion like this. Okay. Give it a heart. So when we take the spin one chain and the Hall chain, you could mimic that by creating a ferromagnetic ground coupling here, and then
If you draw your little circles on the diagonal, then there's a much closer relationship between the two systems, and then you can map smoothly from one to the other.
yeah.
So by this method, can you actually get gapless excitations as well?
Yeah, so I will show this explicitly. So that's a limit where this method starts to work less well. So it works very well, once you have a gap, and that's because you're doing perturbation theory. Okay. So once while you're doing perturbation theory for a gap system, you will find that these series converge very quickly, and you can extrapolate them very easily to this limit. Where lambda is, for instance, 1 in this case. And as this gap closes, you will see that the series will start having a problem, and you can try to overcome the problem. And I will show this explicitly later on. Okay, so next step was, now we're doing this for 2, so we put in.
The O matrix, is that different from the S matrix?
Yeah, so.
Because here you have a transpose.
Yeah, so, it's the simplest case, it's a long way back. So in principle you can do an orthogonal transformation, that's what the O was indicating. And this is the weaker part of a similarity transformation, so in the end it doesn't matter. You can always do an orthogonal matrix there. Okay? So it's so I can delete that. So the reason that we have to do this in the two-particle case is that, see, we have 3 sectors now in here. So there's the ground state sector, which is fluctuating. There's a single particle excitation sector. Now these two have different quantum numbers. So the ground state is a singlet, while the excitation that I put in here is a triplet. But now 2 triplet excitations can form back a singlet. Okay, so there's a common quantum number between these 2 guys, and that's why you have now to keep track and you actually keep them orthogonal to each other. Okay, and, so the case that you're only diagonalizing this part of the Hamiltonian, trying to create a block diagonal form like this. It's a much simpler problem, and you can use a recap transformation to do so. Okay, so now we have the situation that we can put in 2 of these dimers, dimer excitations, triplet excitations. Again, by turning on the coupling along these layers, they get fast, so they start moving around. And in the case of these 2 dimers now, these 2 triplet excitations, these 2 triplons, what we get is scattering between the 2. So the spectrum that we'll calculate looks like this. So there's, I remind you in this energy momentum plot, there is a dispersion of a single trivium, which is just a single excitation, propagating along the ladder. And now if you have two of them, what they will immediately form is a continuum state, so just scattering these two, which you can simply get by taking this dispersion, taking another one of that, one of them together, you have history this. But then the most interesting part is that they can also form bound states or anti-bound states. So beyond this continuum, which you can calculate with just having the information of the single triplon, you can also have these states where two of these triplons now start binding to each other, and they split off a state which is below the two particles. And so the quantum number of that can be a singlet, like the ground state, can be a triplet, which in this case, turns out that there is antiferromagnetic coupling in both directions about bound states, and then it's very visible. There is a state which splits off the continuum above the continuum, which is s equal 2. So quintuplet state, so that's an anti-bound state. Now, there's a lot of experimental simulations where it's very interesting to calculate these states, and that's why I'm showing this. It's very nice to calculate these things. If you can calculate these bound states, you can match them to experiment where they, for instance, measure Raman spectra or something like that, where these bound states will be sharp quasi-particle lines in the experiment. So they will see a scattering continuum, and they will see these states. And when you see those states, we're doing a calculation to predict these energies. We can, for instance, start fitting all kinds of coupling parameters.
What is an anti-bound state?
So, what is an anti-bound state? Yeah. So they this is a state where instead of scattering, reduces your energy. In general, that scattering effectively increases your energy. So it would, an individual would be better off if the other one wouldn't be there. Yeah? So then there's the, but you see the effect is it's much smaller. So all these peel off here, very visibly. It's a much less common. And typically, in experimental situations, you're much more interested in these situations because below, the shoulder of this continuum, you get another sharp line. So you have a single triple excitation and then two of these. Okay. So now that you have seen that one can do the ground state, and a single particle spectrum, the two particle spectrum, you have guessed that we can do even more. So you can go now into three particles and so on, and then the whole form is further expansion. So you can start exploring further down here, and you can calculate triplets and all kinds of things.
How would you calculate the difference between the different spin bound states?
How do you say that again?
How do you calculate the difference in energy or dispersion of these different spin bound states?
So the single and the triplet one?
Yeah, the 0, 1, and 2.
Yeah. So so what you're really calculating is this effective Hamiltonian of these two guys, and you haven't fixed the quantum number. Okay. So you don't say these two guys have to be a singlet or these two guys have to be a triplet. And then as you what you calculated practically is this effective Hamiltonian in the two excitation subspace, and then you diagonalize, and then there's multiple solutions, and you can see that. Now you can go ahead and calculate this effective Hamiltonian, constrain the quantum number, so that you only see the s equals 0 part of the spectrum, or s equals 1 part of the spectrum, and then again pinpoint which one you have actually seen.
So, as you turn on long out, is it possible to see one excitation go below the constant energy?
Below the constant energy? No. So
the method is really converging.
So that that's the same, no. So that it's the same question as that has been asked before. Can you see the closing of a gap? Okay. So so can you see that? And so the answer is well, you can go and look exactly how that happens, how the gap closes. But as the gap closes, you go through some sort of phase solution, and you will find you will never be able to say anything beyond that phase solution. Okay. So there's the other case, so that would be the situation of a continuous phase solution. There's the other case that this actually undergoes a first order phase solution, which is this crossing of energies. So in the way that you're calculating things here, what you're really doing is you're expanding around some unperturbed Hamiltonian, so which says that you're introducing a perspective, a bias into the system which says Now this is, the state I would like to expand around, and then you look, how far I can actually go. So you're exploring basically one phase and potentially its boundary. And now you can start from a different perspective, another Hamiltonian, unperturbed Hamiltonian, and do a perturbation in the other direction. And now if you find a nice crossing of these two Johnson energies, then you have likely a further transition. Or you see two gaps closing.
I was just wondering what you get if you did the perturbation the other way. You start with the interferomantic chain and added the vertical coupling for perturbation.
Taking the whole chain is not typically what they do, because that's a very complicated, many way system already. So, you always take, small subsystems. But you could have done, all kinds of other things. You could have, taken a dimerized chain and, expand and pose in the dimerization of the chain plus, the other thing. In the end, so in these simple cases of, maybe what you state at the end that you're looking at is a gap state. Different perspectives should always end up in the same state if you're studying the same things. So if it's all these different starting points are connected, that should work.
But they may be separated from phase transition, in which case.
Well, if they're separated by a phase transition, then you can only see up to the phase transition. And then if you're starting from 2 points and they they don't meet, then you don't know what's between. Okay, good. So now we have calculated this series, and I mentioned earlier, well, we might want to take a look at these series and their behavior, in particular because we're interested in asking this question: how far out into parameter space is such a series good? So the question is, do the series that are calculating, do they converge, for instance? And well, so first there's some experimental fact here. So if you do a spin system, so a spin S Heisenberg Hamiltonian, you often find indeed that you find convergent series. So here's the series of the constant energy of the Heisenberg ladder that we just looked at. And if you just look at the coefficients, you see that they nicely decay. So that might suggest that these are nice convergent series. And in order to get the constant energy for, in that case, lambda equals to 1, all you do is plug it on there. Well, so that's what this might be suggesting. There's other series, like here's the constant energy for a chain of bosons, as opposed to Hubbard model, where you do your expansion on T over U, so that's lambda, and here are the coefficients of that series. And it looks very awkward. So you will find that these coefficients in this series, they grow like crazy. So just putting in a number that you like for your particular value of lambda might not be very helpful, because it basically just measures what the last coefficient in this series was. So the second series turned out to be an asymptotic series. Its convergence radius is strictly 0. So you're not supposed to take this series and put in a number and get it out. So somehow, you would sometimes get series that are not even well behaved by this very simple consideration of looking how the coefficients grow or decay. So it doesn't tell us about the problem. So it's a second situation of chain of bosons. Is it possible to solve this way? And the answer is no. But what you have to do is now you have to take a very close look at these series and try to extrapolate and re-sum them in a good way to make sense of it. Now, it might sound like magic, but it's a very well established framework. It goes all the way back to those people who have been working in series expansions on statistical mechanics models. And one oftentimes used way of dealing with these series is to use extrapolation schemes. And one of the extrapolation schemes is called a Padé approximant. So let's learn what a Padé approximant is. So let's assume we have some series that we have calculated to some order of lambda, and we would like to guess how the series is going to compute despite the fact that we haven't calculated it. So the situation would be that what I've done before, I've calculated for my spin ladder the constant energy up to order 4, but I would like to know the result of order 5 despite the fact that I cannot calculate it. So I want to guess this somehow. So now I have some series, and I would like to approximate it. This is Padé approximant, which is this quotient of two other series, which come at order n and m. And I would like the Taylor expansion of this series here to match exactly what I've calculated. So here's my setup. So I have calculated the series of some grounded energy function and the first four coefficients with these that I found here. Now I take that as an input, and now I'm saying I want to approximate this Taylor expansion by two series of this form. So let's take an example where n and m, so the order of those series are 2. And well, it's a well-defined problem, and I can solve that without any approximation. So this Padé approximant is uniquely defined, and it has this form. Okay, so you get that by inversion. So if I take these two series now, and I do a Taylor expansion from them, I will find that the first four orders here will exactly match those which I had before. So those are the ones that I calculated for my physics problem. But I can continue doing this expansion, and I'll calculate 5th, 6th, 7th, 8th order for that approximate. And that's really what I'm after. So now this is a scheme of continuing the series that I've calculated in some way or the other to infinite order. And so this is just one way of doing this. So that's Padé 2 to this series. I could have done other ones. Yeah? So, well, which ones could I have done? Well, the two orders that I have here, n and m, in this Padé approximant must sum up to the maximum order that I've calculated for this whole thing to be well defined and be convertible and be calculated. So I could have done a Padé approximant 1, 3 or 3, 1, changing the order of the series in the denominator versus the one in the denominator so that they add up for the end again. So I get different Padé approximants, and well, all these different ones might give similar results as I extrapolate the series or different ones. And one way of looking at this is, for instance, the case that I now take for a system that is gapless. So I take a Heisenberg chain in one dimension, which is a gapless system if you take uncorrelated coupling in these spin on halves. But I start doing the expansion to look at that limit by dimerizing this chain. Well, the dimerized limit, it's again a system which is just a couple of dimers, so that's a gap system. And as I turn on the coupling between the dimers, slowly I will generate the gapless mode. And so what you see here is the result for that excitation, so the lowest triplet excitation, and I plot its dispersion. And the dots that you see here are the 10th order Baire results. And so they suggest that the excitation comes down to some small value as you go to momentum 0. Well, we know that in the limit of infinite order, this system would be gapless. So here you see that even at 10th order, you don't manage to close the gap. So the perturbative expansion keeps telling you there's a small gap. But then we can take the series that we have calculated here and do a Padé on it. So one of these approximative schemes. And then you see that those are already much better in predicting from the same 10th order result that you would like to close this gap. And actually, these approximants nicely show you that.
Sorry, I may have missed. How do you find the P and the Q in general? So how do you find those polynomials?
Yeah. So here's what I want to do. So I want to find the coefficients of these two series. And what I do is I fix the order. Okay. So I have n plus 1 coefficients here and n plus 1 coefficients here, such that when I Taylor expand this series, that the first orders in this expansion exactly mimics these here. Okay? Well, that's a well-defined problem that you can just convert this matrix, and calculate these coefficients here. Okay? But once you have these coefficients, you can continue to Taylor expanding them, and then you go to higher orders. And what I'm plotting now is this function here. So I'm effectively doing this extrapolation to infinite order, and I use it as a second line in my plot.
But that's an invertible process, you're saying?
Yeah, so this is an invertible process.
So you'll find a unique polynomial?
It's that's a unique. Yeah. So that's a unique solution, and but it's very sensitive to these coefficients here. And this is the reason why these Padé approximants are only used in this context of these exact series. So I'm taking a 10th order series or a 20th order series, and I'm doing this Padé approximant. So why is Roger not doing this Padé approximant on this 5,000 orders in his Scottish Monte Carlo? Well, he's not doing that because every single coefficient here that he has a statistical error. Yeah? And despite the fact that he has 5,000 of them, the small statistical error in this inversion problem will have these Padé approximants just below. So they're not useful. Yeah? So in order for this to be a well-defined situation, you want to have some precise coefficients here, and then it works.
So is there a simple way to see like why is that like a sensible extrapolation scheme? Because in principle you can have any series of 4 order and then use another prescription from the beginning and get something else.
So this is just so from the bag of messages, just one. It's a very popular one. Yeah. So because it's well defined. Yeah. So just one way of guessing. What comes next. Okay. And so the practical example is one where you see it does a reasonably good job. Yeah? So this is so and what you would typically do in a situation where you have no idea how well these things are. For instance, in a high temperature expansion, you will do all kinds of different Padé approximants, and you will see that they will extrapolate this series, and then they will start to fan out different approximants that you can do for your series that you have calculated. So I told this pedagogical example of 4th order expansion. If you have a 10th order expansion, you can do it for 5 or 6 or 6, 4. So you have a lot of variations which are all very similar in the end. And you can see when they start to fan out. So that part where the bare series and agrees with the Padé approximant, that's fine. And then you see that it continues on a line where these don't fan out. That's the part that you still take as a good extrapolated region. And you have something like the arrow bar, which is the fan of the different approximants. And you will see that eventually they will fan out very much, and then you stop extrapolating and using these schemes.
Can you just compare now the paper return? How close it is on average?
So yeah, for these pedagogical examples, you could actually calculate the first order term and look so I don't know. So I don't know what the numerical agreement with these numbers is, but what you can do is you can of course calculate higher and higher orders of this expansion. In this case, it's all very well controlled, so eventually this gap will come down. So the blue line, if you would go to 12 or 14th order, will converge to the exact result. And the point here is that you can see that the extrapolation already does this for you at a lower order. So it must do a good job.
Yeah, so my question was how does the red line compare to the beta?
So the beta ansatz would be that you have a straight line which comes, this is a finite slope out of your momentum. Okay, and the fact that the red line still curves in shows a limitation here. Okay. Well, but then the question is you're not interested in these perturbative techniques to beat beta ansatz. But the point is that you can get results which are very, very similar in quality.
So when you do the series expansion, you start from a situation where, in this case, you take diamonds, which is not resembling the physics of the Heisenberg chain. So what you're saying now is that after this curvature, you get the physics when you do this.
Well, so that particular example, of course, is you have a gapless system, but that gapless system is just a neighbor to the dimerized chain. So starting from the dimerized limit and then extrapolating, you can actually you can get back to the gapless situation. Okay, you might have other gap states, and you might which are separated from some other starting point through a phase division, and then this will not work. You will not be able to go through the phase division expansion. Okay, so let's continue with another kind of approximate, and that's called Padé approximant. So let's assume that the series that we have calculated has, for instance, this kind of form. So we have some critical point in our parameter space. So for some lambda, there's a critical point at which the series becomes 0, and there's some exponent. So that's for instance where a gap closes. So what you can now do is you can make an Padé approximant instead of to the bare series. that you have calculated to its to the differential logarithm of that series, and then you will see that if you do that from this form, this Padé approximant will have a very nice and simple form, and that you can calculate, for instance, this critical point is a root of the denominator series of this Padé approximant, and you can calculate that exponent as a residual of that Padé approximant. And we can again look at an example to see how well this works, which is again coming out of the world of the spin chains. So now we take our old spin chain again, the Heisenberg chain, we have uniform coupling, and we turn on a second nearest neighbor direction, coupling every other spin. Now this system is well known to undergo a transition for some finite coupling strength of this second order next nearest neighbor coupling. So here's one plot showing that used so that the excitation gap in this spin chain, which remains zero for as you introduce this translation, coupling antiparamagnetically to the next nearest neighbor for some alpha. So the original Heisenberg chain, which is gapless, remains intact for a while, and then eventually you drive a transition into a gap phase, which is a dimerized phase, and it's very well known that if the coupling strength between these two guys is exactly 1/2, then you can solve the system exactly. It's my Bosch point of this chain, where this dimerization pattern, down in every other bond, is an exact ground state, and you have two of them. So you could try to calculate this in the series expansion by starting as before. You're starting from a dimerized limit. So that's a simple limit here. So you put the dimerization on every other bond, and that's your starting point. So you're starting effectively in some gap phase, which is very much like this phase over here. And then turn on both the coupling between these dimers and the next nearest neighbor coupling. So your Hamiltonian will be split in this way. So you have simple dimers, that's your unperturbed Hamiltonian, and you have both the next nearest neighbor coupling and every other dimer coupling as a perturbation in the system. And now we can look at this phase transition. And so this phase transition is driven by a marginal operator in the Heisenberg chain, which becomes relevant at this point, and the gap opens with a particular exponent that you can all calculate if you use other techniques such as conformal field theory very well. And so now let's try what you would get if you do the series expansion and use these extrapolation techniques, using this d-log Padé approximant. Okay, so the first thing we can do is we can calculate this situation again, but for no nearest neighbor coupling. So let's see the dimerized chain. And what's plotted here, d-log Padé approximates to a 10th or 11th order series. Let me see. So it's a 10th order series, and there is different Padé approximants shown here. So n in this column, in this row here, is 4, and then so this is the d-log Padé approximant 2, 4. This one is 3, 4, 4, 4, and 5, 4, and so on. And there's two values given in this table. The first one is at which value of lambda is the system going gapless. And you see that these numbers are all very close to 1, as it should be. Yeah? So for equal coupling between this dimer here and this dimer here, the system becomes gapless if there is no next nearest neighbor coupling. And doing this d-log Padé approximant, you can also calculate how that gap flows is. And the exponent that you get turns out to be this 0.74. So that's one number here. And now we can go to the point where the system opens up the gap, so you go exactly to the transition, which has been determined to great lengths, has a critical coupling. So the critical coupling is something like 0.24 something. And again, you can do the same analysis, and this d-log Padé approximant again tells you that the point where the system becomes gapless, you're starting at the dimerized phase, is for lambda equals to 1, but now the critical exponent comes out very nicely to be close to 2/3. That's exactly the conformal field theory prediction. So so that's the average over all these numbers in brackets, which are giving the critical exponents for every single approximant. Okay? Now you see that some of these approximants carry a star. Those are the ones which this language I call defect approximant. Those are the ones where you not only have a residuum close to 1, but a second one for lambda smaller than 1, which means that your series diverges before you actually hit the point that you're becoming close to what you expected, lambda being to 1. Now, so that's interesting. So you see that at the phase transition, you indeed recover the 2/3 exponent that you would expect from other means, such as conformal field theory, while for the original unperturbed Heisenberg chain without any next series neighbor coupling, you do not recover the same exponent, which you actually should. So in both cases, the instability will open a gap. The exponent is 2/3 because it's the same conformal field theory, the same relevant operator you use to destroy that gapless state. The reason that you see a different exponent here is that, well, as I said, there is a modular operator, so there's a lot of logarithmic corrections in that Heisenberg chain, and all these logarithmic corrections you cannot capture using these Padé approximants, which all assume that you have some nice exponents and no logarithmic corrections. What the point where you go from the Heisenberg chain to that dimerized Newton-Roche-like state, that's a point without logarithmic correction. At that point, you can actually see that exponent very nicely using these theorems. Okay, so the takeaway message is that you can also use these techniques to identify very precise and locational critical points, and even get stuff like critical exponents out. Now, as I'm coming to a close, let me mention some more general situations where these techniques are used. I use these very pedagogical examples of one-dimensional string chains as examples to show how this technique works. That's probably not the context that you really want to use it. Probably the nicest playground to use these techniques is in the general area of frustrating magnetism, which are generally higher dimensional problems, yes, 2 or 3 dimensions, and we're interested in calculating effective Hamiltonians pretty much in the same way as we have done when we consider the situation of these triple excitations on our lattice system. We have a degenerate subspace, and within that degenerate subspace we were interested in calculating some effective Hamiltonian again, up and solving allowed us to calculate the spectrum there. Now this is very reminiscent of the generic problem in the context of these frustrated magnets, where the frustration leads to some sort of degenerate manifold of states by some bare coupling in the magnetic model, and then you might have some other smaller couplings that you're interested in asking, what is the effect of these smaller couplings on this degenerate subspace. So you're interested in calculating effective Hamiltonians in some degenerate subspace, and then solving that effective Hamiltonian. But what a link-cluster expansion can do for you, it can help you calculate that effective Hamiltonian. That's probably the way that these things are used prominently in these days. And this situation should be distinguished from a situation where you're not only interested in the splitting of some subspace of degenerate states, but from a situation where you actually try to calculate an effective Hamiltonian full Hilbert space, which couples this degenerate subspace also to the rest of the states in your Hilbert space. And the second scenario is much more complicated, and finding a good way of calculating these more general effective Hamiltonian is a more complicated issue. There's a very nice recent review, a book chapter by Frederick Millar and Kai Schmidt on this more general perspective, which I urge you to read. Let me close by showing you one example out of this world. This first example, you have some degenerate subspace of states that you're interested in calculating an effective Hamiltonian and then diagonalizing that and thereby distinguishing different degenerate states. And this comes up in a classic model of frustrated magnetism, which will be reiterated probably several times during the school. For sure, Andreas Leuke is going to talk about this problem, which is the Heisenberg magnet, which is a hard problem. And so we're interested in finding its ground state. And it turns out that it is not as straightforward as on the bridge. So there's many different possible states that are good candidate states for this ground state. And so very recently, Raju Singh and David used a very nice approach to this including these series expansion techniques, and here is what they have done. So what they considered is for this carbon lattice, they consider different diamond coverings. So diamond coverings are singlets. So every singlet is a diamond in this picture, and every vertex is part of exactly one diamond here. So one singlet. So we have this covering of the carbon lattice by dimers, and well, there's many different ways of putting a diamond covering onto this carbon lattice. So this is in principle the degenerate subspace that you're interested in analyzing, and we are now interested in finding out which one of these diamond coverings is the lowest energy state, and is that probably the most likely diamond covering ground state. Now, the two candidate states that these guys looked at are called the honeycomb 1s1 crystal and the stripe 1s1 crystal of these perfect hexagons. So if you look at these simulations of these diamond coverings, you will see that there's these little hexagons, and these hexagons have 3 diamonds covering them, and now you can make different patterns out of these hexagons. And so one situation would be these stripes, so they align like this, or this other situation where they form a honeycomb lattice. So if you look carefully, you will see that these perfect hexagons form these plackets here next to each other, and then they form a nice honeycomb lattice. This first state also goes by another name. It's a pinwheel state. If you look at these plackets of the honeycomb lattice, you'll find that there's a diamond configuration in there, along such a pinwheel here, and there's a resonance state of that pinwheel, which allows the diamonds to fluctuate back and forth, like in the solar ring, and so it's often also described as a pinwheel state, but these guys have good reason to call it the honeycomb 1s1 crystal, because from their perspective, they like these hexagons, because they come up in perturbation theory. You hear how it works. So you take the diamond covering, and you start doing perturbation theory, and you can do this. So the elementary building block in their calculation are these empty triangles. So those are the points in their diagrams, and so they look what happens. So if you do a second order perturbation theory in the coupling that, so now you have a diamond covering, and that's your unperturbed limit, and then there's all the other bonds in the carbon lattice. That is the perturbation now around that diamond covering. So you see that in second order you start favoring these empty triangles, so these little triangles with there's no dimer sitting on the triangle. So they come in naturally in second order. And so dimers resonate along those, and they're energetically favored. So you see that there is a pattern of these empty triangles in both of these states.
Sorry, do they project in the S equals 0 subspace, or do they 1 minus lambda, 1 plus lambda that we did in the previous space?
No. So they start with a dimer covering, which is in the spin singlet state. Yeah, but then they take all these fluctuations that come about. Which will peak always in the singlet state. Yeah. So what you have a triple explanation, there's a virtual explanation there at the back, and this is the reason why the first term that comes in is in second order. Now in third order, you have this formation of these perfect hexagons. So 3 of these empty triangles like to arrange in a way that they give rise to this grayish area in between. So in third order perturbation theory, those states are favored, but there's no particular pattern associated. Whether they are in this honeycomb lattice or in this stripe lattice. Okay? And then as you go to fourth order perturbation theory, this is where you start lifting the degeneracy of these states by having these red bonds. So you start resonating along these red bonds, and you would like to have as many of those as possible. Now if you do a careful counting, you will see that in this picture up here, there's many more of these red bonds than on here. Now, I lifted this lower picture from a paper from Sentin and Nicola Pedic, and while in their particular stripe covering, they have some of these perfect hexagons split. So that there's no of these red bonds here connecting 2 of these red empty triangles. So this state is certainly disfavored over a more regular pattern of these stripes. But even if you take a regular pattern of these stripes and you maximize the number of these red bonds connecting these empty triangles, you'll find that the number in this picture turns out to be lower than here. So it is in forced order that you start to distinguish these two candidate states. There's this stripe configuration, there's this honeycomb configuration. Now in their calculation, the natural building blocks are these empty triangles, these hexagons, and you have these red bonds coupling these empty triangles. And that's why from their perspective, this state should look honeycomb state, because that's what they see, the formation of these honeycomb layers. And the consequence of that then is that you get these pinwheels. But it's not that, as they build up order by order, they actually see that the pinwheel is a perfect thing to have. They see that, everything that surrounds the pinwheel is good to have and lowers your energy. Now, in this situation, so these are the bare numbers that you can calculate in the series expansion. This is yet another way of looking at it. It's much elegant. So, you can go order by order through the expansion and add it up, and then as you compare these two states, with this honeycomb state, the pinwheel state, and the stripe state, you'll see that the honeycomb state has a slightly smaller energy. When you do the calculation of the thermodynamic limit as compared to the stripe state. And then there's a third calculation here, which is 36-side clusters, so you just take the largest cluster that they can do their calculation, and instead of doing this transformation to the thermodynamic limit, you just take the bare result that you get with that big cluster and compare that. And you can compare these things to other calculation approaches, like the extrapolation energy that you get from exact normalization, which you will find is very similar. So these are the two numbers that should be compared. So the calculation from the thermodynamic limit, so the series extrapolated number, well, here there's an extrapolation, they just plug in number equals to 1 in their calculation, and the finite size extrapolated number from the extrapolation, so they come out very close. And also the two numbers that you get when you look at the finite system, if you look at the 36-side cluster in the extrapolation, you don't do any extrapolation, you just take the bare number and compare that to the series expanded result from that. You should compare that to the other candidates. Good. Well, and then there's all kinds of other approaches which also try to solve this problem, and they find states which are similar or dissimilar. So something that you might hear later on in this series of lectures is an approach called multi-scale entanglement ansatz, or MERA. And these people give it out, and student Van also looked at this carbon lattice. They have a different bias in their calculation. They're looking for a low entanglement state. Well, these diamond carbons are such low entanglement states, and they also find the same honeycomb or pinwheel state as this one, and their energy is an exact upper bound, which again is very close, to these numbers. So in the end, you have to get all these states. And then locally here, Mike Hamilton and a lot of other people look at a much simpler variational approach. A good scalar projected waveform study, which gives you one liquid possible ground state, which is slightly higher in energy, but you shouldn't take it as a bad result. They have so many less variational parameters. It's actually pretty cool that they can, have an energy which is so low and so comparable to all these other states in this problem. So this is very nice. It's a very different concept. So what this tells you that there's many different concepts. So there are many different low energy states in this carbon situation. Andreas Leuchi is going to discuss this in much more detail in his lecture on applications of exact normalizations. Where you can see these things. But there's also a contribution coming from the series experiments. I'm not sure about the original one. You can distinguish these different diamond coverings to do a careful experiment. Now, let me give you some idea about future prospects. Topic to write this thing, who has been working on this field for a long time, he makes the following observation that whenever you get 5 more terms in a series for a given problem, this ends up, you getting a different perspective on the problem, so you get deeper insight. So this is what you should be aiming for. Now, that's a hard calculation to do. 5 more orders means that you have to take, many more diagrams into account. And every diagram you have to do, these calculations, which also, these perturbative calculations, you have to go higher and higher and higher orders in your perturbative expansion. And that's generally hard, and that's the limitation of this approach currently is, so you have memory limited in doing these largest cluster perturbative expansions. Now, the other thing that is interesting about series expansion is that they can be highly parallelized. There's a very natural way of being parallelized. There's, we've already seen, all these different clusters and diagrams that you're supposed to do calculations for. So If you go to the cubic lattice, there's about 1,000 diagrams that you should be calculating in 10th order. Well, all these calculations you can do in parallel. So there's no reason for you to wait, for the result of another calculation by doing one of these diagrams. Only in the very end, you have to combine these results and do the subcluster subtraction and add them up to get the result in the thermodynamic moment. So this makes these series expansions an interesting candidate to be one of those techniques that you can actually port to these extreme computers that Thomas Lewis has been talking about. And people have been trying now to bring this into petaflop computing, these series expanding techniques. And the reason is that going to these very big computers, you might have the chance of going to these 5 more terms. So what he's estimated is that for the 2D TJ model, it might go better to the order 15 is something that we're doing high temperature series expansion. And for the triangle IS model, even go up to 18th order in the high temperature expansion, which is very elegant. The high temperature expansion is the least biased way of doing these series expansions. And it would be nice to have results. Good. So while it's an old and very traditional technique, you might be using it on the others of new computers these days. Let me very quickly flash some alternative approaches to these series expansions that I've been mentioning here. So one is called numerical link cluster expansion, something that Roger Singh and Marcus Vidal have been developing a couple of years ago. And their idea was to, so why calculate only a finite series on a given diagram? Why not take everything that I can calculate on a diagram? For instance, I could do exactnation on every diagram to take all the information that I have and try to put that into the final series. So I take more information for every single diagram than just limiting it to some finite order. Turned out that's a good idea sometimes. It helps you to go to lower temperatures if you do a high temperature series expansion, but you lose one of these nice things of the series that you have seen here, that you have a symbolic form. There's an alternative approach called continuous unitary transformation, or shorter cut. It's something that goes back to Franz Wegener, who has been working with this in Heidelberg for quite a while. It has been independently developed by Wilson, and in the last 10 years, Götz Urigen's group and Kai Schmidt have been working with these techniques quite extensively. It's a very similar way to calculate an effective Hamiltonian in the way I described it here. It's a technique where you again want to block diagonalize your Hamiltonian. You do this in a continuous unitary transformation, that's the name. A large number of infinitesimal steps. Eventually you will end up with such a block diagonal Hamiltonian, which is exactly the same form as the one that I would have been deriving with these techniques that I described. Because some reminiscence of renormalization techniques, it integrates as high energy terms first and then lower energy terms in the very end, the block diagonalizing, and so that's probably the reason it is. And finally, I mentioned another technique called conductor renormalization of core, that you should have at least heard about, developed by Moniker and Weinstein back in the 90s, which is a non-perturbative approach. That's the real difference to this that we have heard before in generating effective Hamiltonians for some system that you're interested in. And it's another way of doing real space block designation to get these effective Hamiltonians. Probably Andreas is going to talk about this as well. Because it's a non-perturbative technique, you can do things that you cannot do necessarily with perturbative expansions. For instance, these effective Hamiltonians might be valid in all regimes of your parameter space, and particularly across quantum phase conditions, which set a natural limit to these perturbative approaches. Good. So at the end, this short summary of the cluster expansion. It's a control numerical framework, which works very nice for systems that exhibit gap phases. Sometimes you can use a system that eventually become gapless. It's a calculation with thermodynamic limit, which is also unique to this approach. So you're doing a calculation for the largest system you can possibly imagine. And it has all these close connections to graph theory. The advantage is it doesn't have a sign problem for fundamental, so you can apply all kinds of problems that are limited from that perspective. So that's what you typically use them for. You're not limited to any dimension. You can write out your diagrams in 1, 2, 3 dimensions. But it is a perturbative approach, and that has a limitation. And you know, you have to go through these steps of extrapolating the series, and you know, it's somewhat magic. In the end, it's very helpful. I will stop and give you some references. Most importantly, there's a very nice book from an Australian group on John Altman that summarizes all these things. Okay, thank you.
So, can you use this to describe topological phases, or is there some reason why that doesn't?
Well, so you can do a calculation in a topological phase. So people like Kai Schmidt, they have done calculations of lengths in the theory code and put an excitation in, and you can look, how that excitation is dressed. It's not a good technique to see a topological phase in the first place, because you see it has a very local perspective on the thermodynamic limit. So it starts by exploring the immediate surroundings, but the topological self itself somehow reveals itself only in the thermodynamic limit as you cross some boundary. So certainly that is not possible. But what is possible that if you're in a topological phase, you can talk about excitation phase. So it's like a topological phase without seeing separate.
But can I say, start with a topological phase and compute this ground state energy perturbably
Yeah,
and compare
so,
to something?
Yeah, no, so you can go into one sector and calculate the energy, and you'll get a good result. And you can take an excitation in that sector, unless you don't close the gap of the topological phase, you should be doing a reasonable calculation. And that has been done for the theory.
Is there any potential value to some of these graphs using Monte Carlo sort of as a spirit diagrammatic method?
So what is the question?
So here is something like explicitly, right? You're
Yeah.
principally, you could simply do Monte Carlo and get a much higher order.
Oh yeah. So what's the difference between Monte Carlo sampling of diagrams and this explicit calculation? Well, the difference is, that this explicit calculation can be done for any problem. And you get a precise and correct result. Okay, so up to the order that you can calculate. While the stochastic series expansion or a diagrammatic Monte Carlo is something that you can do, for certain problems, and then you can hit it hard and go to very low temperatures.
So this is the extrapolation is scheme depends a lot on how the zero temperature phase ends, right? So if you're thinking from the beginning that it ends in a critical point, then you use that logarithmic extrapolation.
Yes.
But if you don't know beforehand if it's a first order transition or
that's all correct. So it's not a totally unbiased situation. So first of all, you were starting, doing your expansion around some limit that you deemed, useful, and then the way that you extrapolate these series again, you make assumptions. So you try, to see whether it closes, and it might be closing of that particular form that the Padé approximant will get you, the critical point exponent of the gap opening. But you will see that it will work very well in a situation where you actually, do the right thing from the right place, and it will, dramatically fail in other situations. But it's, the zero temperature expansion that I'm showing here is not an unbiased technique. But it, that shouldn't sound too scary. Lots of things have, some bias, and I'm just very clear about this. So, as I said, other techniques are variational. Other techniques, prefer low entanglement states, and so on. So they all have some sort of encoded bias in it. The most unbiased expansion is always the high temperature expansion. So, is that what you wish for? You should do that.
So in case you're biased, say you expect a first order transition beforehand by other arguments, if you're expecting a first order transition.
Yeah, so if you expect a first order transition, what you should be doing is start calculating from those limits, and what you will see is level crossing. And well, you will see that, and then you can be remarkably good in identifying the condition and its location, and the fact that it's first order. Okay, so let's close and.